Alright, so for this next part, we're still going to be dealing with the situation with the bar, where we know the temperature at one side, the other side, and the initial temperature, and we're trying to figure out how heat diffuses through it. Last time we did an explicit solution to the problem. This time we're going to do the Crank-Nicolson solution, which is an implicit solution. So we're going to start out kind of the same, where we have the heat diffusion equation only in the x direction. Again, with no heat generation or anything like that. So we have that, and then we're going to, again, split the bar into sections, split time into increments, and end up with this approximation. And I derived that all out in a previous video, and I just have it rewritten here. Last time we ended up using a relationship of R, but this time we're going to use U, and that's right here. Okay, so we start with this, and the way that Crank-Nicolson works is that for this term, instead of it just being like this, we're actually going to take an average between this term at n and this term at n plus 1, so at the next time and the current time. So we can do that up here. So we have that alpha over 2, because the division by 2 is going to be for the average, because we'll have two terms added and then divided by 2. That's how you take an average. So I'm going to put the 2 here so don't forget about it. And then the first term is going to be this one, just how it is. So t at j plus 1 at n minus 2 times t at j at n plus t at j minus 1 at n. I should just put it. Okay. Over delta x squared. And then we're going to add to this the same thing, but at n plus 1. So to do that, we're going to have t at j plus 1, n plus 1, minus 2 times t at j at n plus 1, n plus t at j minus 1, n plus 1. And that is going to also be over delta x squared. And then, I do not know, that's an equal sign. Sorry, I wrote that weird, but that's an equal sign because that's an equal sign. Okay, so then there's that. And I'm going to put the equal sign on the other side because I'm writing out of room over here. So equals t at j of n plus 1, t at j n plus 1 minus t at j at n over delta t. Alright, so this is now the Crank-Nicolson method where we have this average. So we can simplify this a little bit. We're going to use this u term to simplify things. So we have this alpha. We multiply the delta t over. We've got the 2, and factor out this delta x squared. We'll get u over here. So we write it like this. So t at j at n plus 1 minus t at j at n is equal to u times t at j plus 1 n minus 2 times t j at n plus t at j minus 1 n plus t at j plus 1 n plus 1 minus 2 at t j n plus 1 plus t at j minus 1 n plus 1. Alright, so like that. So then, next thing, we're going to factor this u into all of these terms. So tj at n plus 1 minus t n is equal to u times t j plus 1 n minus 2u at t j n plus u t j minus 1 at n plus u at t j plus 1 n plus 1 minus 2u t j n plus 1 plus u t j minus 1 at n plus 1. Alright, so next thing we're going to want to do is we're going to split these into two sides. So we're going to put everything that is n over here. So we're going to put all the n terms over here. And we're going to put all the n plus 1 terms over on this side. So I'm going to start with the n terms, and then I'm going to mark them in red so that we can keep track of everything and make sure everything gets to where it's going. So that's n plus 1. We're going to save it for now. So we've got, this is n, that's n, that's n, that's n, and then this is n plus 1, n plus 1, n plus 1. So we're just dealing with these ones. Okay, so then within these we have jn, j plus 1n, another jn, and j minus 1. So, so we'll start with this j plus 1. So subtract it over this side, we've got negative u at t, j plus 1n. So we've got that one, and then we'll do just this jn. So we subtract this one over, becomes a positive, so 2u, so it's going to be 2u minus 1 times tj at n. And then, so we got those, and we need this one, subtract it over, so minus u t j minus 1 at n. Okay, and so then that's that side. Now we need to do the other side. Alright, so for this side, we've got this term, that one, and that one. Alright, so again, we've got a j plus 1, 2 j's, and 1 j minus 1. So we'll start with j plus 1 again. So that's on the first side, so we'll keep it. Alright, and then we got that one, then we got these two. So this will be 1, so we'll subtract this over, so we'll have negative 1 minus 2u times t, j, n plus 1, and then, so we got those, and then we're going to just keep this one like it is. So it's plus u with t, j minus 1, n plus 1. Okay. And then I think I'm going to multiply the entire thing by negative 1 to make this a little bit nicer. So we're just going to multiply both sides by negative 1 so that we can get, so that way we get u at t, j plus 1, and plus 1 minus 2u, because the negative will flip that, at t, at j, at n, plus u at t, at j minus 1, at n. And then equals negative u at t, at j plus 1, n plus 1, plus 1 plus 2u t j n plus 1, but minus u, tj minus 1, and plus 1. Okay, so here's our equation that we have, like that. And you'll notice it's pretty complex, and there is a lot of things that we don't know within this formula. So how we're going to solve this is going to be by using a matrix. So in this matrix, we're going to be solving for temperatures. So we're going to be solving, so we'll have our temperature at 1, our temperature at 2, and these are j's. This entire row is going to have T equal to m plus 1 delta T. So they're going to be the ones on this side. So T1, T2, T3, all the way to T n minus 1. Or, I guess it's j minus 1, I think. Because n is already there, so this is j minus 1. Okay, make it bullets. Alright, so then, so these are what we're solving for. These are our unknowns. And then we're going to multiply this by another matrix. And then we'll equal a different matrix. Alright, so I'm going to make some lines. It's a little bit easier to follow. Okay. Alright, so just making rows so that we can kind of follow across. Okay, so we're going to ignore the first temperature for now, we're going to look at the second one. So for the second temperature, so we're looking at this side of the equation because we've got n plus 1. So the first term we've got here is T at j plus 1. So at the second temperature, that's going to be temperature 3. Actually, we're going to want to start from this side of the equation and go that way. So at temperature 2, this is T at j minus 1, which is temperature 1. So to multiply by temperature 1, we're going to want to multiply by this negative u. So our first term on here is going to be negative u. And then we're going to have this, which is just Tj, which is just Tq. So, or T2, so to multiply by T2, we're going to want 1 plus 2u. And then this term, we're at temperature 2. 2 plus 1 is 3, that's temperature 3. So multiplied by temperature 3 is negative u. And then the rest of the values in this part of the matrix are going to be 0. So next row, we got temperature 3. So for temperature 3, we can do the same thing. So 3 minus 1 is temperature 2. So, but the first row is what we're multiplying by temperature 1. So we're not multiplying anything by temperature 1, so that's going to be 0. And then this row is going to be the negative u for multiplying by temperature 2. So then this one is temperature 3, so that's next, which is 1 plus 2u. And then we'll multiply it by temperature 4, because 3 plus 1 is 4, so negative u here, I'll put that 0 up there. And then I'll do one more for us, so temperature 4. So temperature 4, we're not going to go, so the lowest one we're going to multiply by is temperature 3, so not 1 or 2, so the first two values are both going to be 0. And then we're going to multiply temperature 3 by negative u, we'll put that here, multiply temperature 4 by 1 plus 2u, And so this would continue going on, and you can see we kind of have this pattern where it's like kind of diagonals of the same thing, and it would keep on going, getting bigger, but I don't really have enough room, and I think you can see the pattern from just this. So that leaves us to deal with is the first temperature and the last temperature. So for the first temperature, I guess for these we can fill out this side first. So temperature 2, we're now dealing with this side, and these are all known because that are at our current time. These are in our next time, so these are fine. We don't have to multiply them by anything. So at 2, so we've got u 2 plus 1, so that's, or again, we're going this way. So 2 minus 1 is 1, so that's going to be u at T1 plus 1 minus 2u at T2, and then this u at T3. And then we can continue doing that for T3, so this will be u at T2 plus 1 minus 2u at T3 plus u at T4. And all of these ones are going to be at temperature equal to m delta T. So then again for 4, we've got u at T3 plus 1 minus 2u T4 plus u at T5. Okay, so now we get to deal with this first temperature. So the important thing about this first temperature is that temperature at 0 is always known, regardless on the time. Regardless of the time it's at, the temperature at position 0 is always known. My camera's glitching a lot. I'm going to try to fix that. Alright, so then next, so we're going to deal with this T1 here. So the important thing about T1 is that the J-1 term is always known. And so we don't have to have it over on this side because we don't need to multiply it by some unknown T0 to solve for T0. We know what T0 is, so we're actually going to subtract it over onto this side and just deal with these two equations over here for now. So that means first thing, we're just going to be multiplying by T1. So that's 1 plus 2u. And then T2, because 1 plus 1 is 2, negative u. And the rest of these will be 0. And so you can see that kind of still follows the pattern, even though we're not dealing with this term yet. So now, this time, we start with this term and this term, because regardless of what n is, t at 0 is the same. So this term and this term are actually the same for t1, or t1 minus 1, t0. So if you subtract this over, that's actually going to be 2u times t0, and then the rest goes on as follows, so then that's plus 1 minus 2u times t1 plus u times t2. Alright, so then that's how we do the first row. Last row is going to be similar, so, but this time it's not this term that's known. This term, it's this term that knows, because t at, so it's j minus 1, so the temperature at j, that's the very last temperature we have on the bar, that temperature is also always known. So that time this time that one's going to go for that side. So there's basically have like a whole bunch of zeros, you know, however many we end up having for all the rows, and then the last two are going to be this negative u, and then this 1 plus 2, so it's going to be negative u, and then 1 plus 2u, and it won't have the last u. But it's important to note that these are not like lined up with these rows. They're like, you know, all the way down here because of this dot dot dot, and that dot dot dot. The matrix is actually much larger, so that's important to know. And then, so over here on this side, so we've got our u times tj minus 2, so we'll just do that. So u t j minus 2 plus, this one's the same, so 1 minus 2u at tj minus 1, and then at tj we're again going to have 2u, so plus 2u at t of j. Alright, and so this is kind of the matrix that we're going to use to solve via Python the Frank-Nicolson method. Alright, so next we're going to create a temperature profile similar to the one that we did for the explicit differencing, but this time for the Frank-Nicolson implicit differencing. So first thing, we need to import another library. So this time we're going to go from scipy.linear algebra. We're going to import solve banded. Alright, so enter that in, and I'll explain what that is in a sec. So after that, I'm actually just going to kind of copy what we had for the explicit, because a lot of it's the same and I don't want to type it all out a bunch of times. Okay, so we have all of this. All this information we're going to keep the same for the problem. But this time we're not dealing with this value r, we're actually dealing with u, which is alpha times delta t over delta x squared over 2. So now we have u, and then this will all be the same. This will obviously be different. But then other than that, it's the same. Okay, so now we need to deal with the solve banded. So what that's going to do is it's set up to solve something that has kind of these diagonal bands of non-zero values, which is what we have in this problem, so that's why we're going to use it. And to do that, you need to input an array of what these bands are, so we need to set that up. So let's call it an array of bands, and this is going to be equal to mp.0, so we'll fill it with zeros first, and then we'll update the values that aren't zeros. And then within this, it's going to be a two-dimensional array with 3 rows, because we have 3 different distinct non-zero bands. And then we're going to have it at a size n minus 2. And we have it at a size n minus 2 because we know t0, which is up here, and we know t at j, which is down here. So we know both the endpoint temperatures, so they're not being solved for in this matrix, so the size of this matrix is n minus 2. Alright, so then we'll set a bands of might be, okay, I'm just gonna, okay, so the first row and So in the first row, we're going to have this top band up here, which is negative u. We're not going to put it in for all of the values though, because in this first column here, there is no negative u up at the top. It starts out 1 plus 2u. So we're not going to include 0 in this. So u's not in that first one. So that means that we're gonna, so it'll be the first row and it will be actually it should be row 0 because indexing starts at 0, and then it will be from index 1 to the end. So not including that first 0 index, but just 1 to the end. Alright, and so then we can do the same for the next. So we have A bands, and this time we're going to have from, it'll be that second one, which is index 1, and this will be equal to 1 plus 2 times u, because that's this middle band. You'll notice that this middle band starts, this first column has it at the very top, and the last column has it at the very bottom. So this can be for all of the rows of this matrix. So then, finally, we have one more band, and this is 2, and then this one is also equal to negative u. So that's this one here, and you'll see that it's not present in this last column. So we'll go from the beginning to negative 1. So 1 from the end. Alright, so now we have our array of bands, and we can work on this array on the right hand side. So this is something that we're going to want to calculate iteratively, so we're going to put it inside this for loop. And so we're going to call this right hand side. And then this, so ignoring the top one and the bottom one, everything in here is exactly the same, and then the top and the bottom are the same except one of the values has a multiple of 2. So we're going to put all the values in as these middle rows, and then we'll update the first and last one to account for that extra of the 2, the extra t0 and the extra tj. So to do that, we're going to, so I'm actually just going to copy from up here that equation, because it's essentially the same thing, where we have our constant times this, the t shifted one direction, and then 1 minus 2 times our constant and the t, and then the u times, or the constant times the temperature shifted in the other direction. So that's basically the same thing, so I'm just going to copy it down here and change out all these r's for u's. Alright, so then we will update the right hand side, the first value. So then that first value is the same thing times, so that's just going to be the previous right hand side value plus, and then t0, which is shifted in the left hand direction, so that's this one. And then similarly, we'll have the right hand side of the last value is equal to that right hand side of the last value plus this time we have it, an extra one of this shifted to the other direction, so we'll copy that. And here I didn't get that U. Okay. So then we have all of our stuff, all of our matrices defined, so we can move on to the solve banded. So this will update the temperatures from -1 to 1. Or not -1 to 1, sorry, 1 to -1. So that's all of the temperatures except the first and last one, because the first and last one are kept constant. Then, yes, then we'll do solve banded. And so the first thing we need to supply is how many upper and lower bands that we have. So essentially it assumes that we have one main band, and that's going to be our 1 plus 2u. And then we have one band above that, which is -u, so it's 1. And then we have one band below that, also -u, so that's also 1. Alright, so then it also needs us to supply what our bands are, so that's A bands. And then we need to supply this right-hand side. Alright, so then, similarly to last time, we're only going to plot temperatures, or time steps that are divisible by 25, so that we don't end up with 500 separate plots on the graph, because that would be hard to look at. Alright, so we're going to shift enter on that. I didn't shift enter up here. Alright, so then we still have this error here, and that's because right here, I'm multiplying it, basically this one element by like all of the t elements, and that's not really how that works when we really, in fact, just want to multiply it by one element. So, you know, this one has an extra t0, so I just have to multiply or add this ut0, not u times all of them, because we're only looking at one element, so we only multiply by one element. Here we're multiplying by all the elements, so we multiply by, you know, all the elements. So, similarly for the next one, this is just -1, the last value. So, alright, so now shift enter. That should be colon. Okay, now we should be good, and we can check our figure. Alright, and you see we get a figure very similar to our earlier figure. And this time we can check to see if it's stable. Because remember the last one wasn't stable, because when we set dt any bigger than 0.5, say 0.8, we would get a weird mess of function. But this time, if we set dt, and again, as we're setting dt, we're really setting this u or above the r value, but we just put everything else in there as 1, so it doesn't really matter. So dt is the one that's shifting things. So in that time, we can see that even if we go up to 0.8, it still looks stable. We can have a time step of say 2 seconds, and it's still going to be stable. So that's a really nice thing about this method, is that it's stable no matter what. Of course, the bigger time steps that you take, the less accurate values you're going to get, but it will be stable. It's never going to go, you know, all the way to infinity, or, you know, crazy highs and lows values. So, yeah, there we have Frank Nicolson.